Hey there. Ready to decode the world of algorithms?
I like that, decode the world of algorithms.
Because today's deep dive takes us into this fascinating world of algorithms. The ones
Yeah.
that always seem to pop up in those, especially those big tech,
The big tech giants, yeah.
tech giant interviews. Yeah.
Absolutely, those are the ones.
But here's the thing.
Okay.
These aren't just abstract concepts that you need to just ace the interview, right? They're
They're
actually
really the backbone of so much of the technology that we use, like, literally every single day.
every single day. Exactly.
Yeah. And understanding them, it's almost like you get this backstage pass to see how all this technology actually works, which is pretty cool.
It really is. It's amazing.
Right.
So we're diving into a must-know list today. From, let me see, it's a website name, and it's like an algorithm cheat sheet, they're calling it,
Oh,
for
yeah.
interview prep.
Yeah, yeah.
And get this, it was published just recently on October 21st, so it's really up to date. Wow, hot off the presses, basically.
Right.
So our mission, if you choose to accept it, is to equip you, our listeners, with a super solid understanding of what these algorithms actually do, how they work, under the hood, and maybe most importantly, where you actually encounter them out there in the real world, not just in, some theoretical sense. So shall we jump right in?
Let's do it. Let's dive in.
All right. So the first one on this cheat sheet is binary search. Have you heard of this one?
Binary search. Yeah, binary search is a classic. It's like a foundational algorithm, and there's a good reason it's on all these cheat sheets.
Okay, so it's like the Beyonce of algorithms. Everybody knows it.
Exactly.
So how does it work?
So imagine you're trying to find a specific page, but in a massive book, right? A really, really big book.
Okay, got it.
It has to be perfectly sorted, like every page is in order. Now, you could flip through it page by page, but that would take forever.
Yeah, who has time for that?
Exactly. Binary search comes in, and it lets you repeatedly, cut the number of pages you have to look at in half.
Yeah.
So you're basically zeroing in on that page super efficiently, even in a massive book.
That's brilliant. So you're narrowing down the possibilities with every step.
Precisely. And the article even gets into the nitty-gritty of how efficient it is.
Yeah, it mentions something called O log n time complexity.
Yes, that's the technical term. But basically, it means that it's really, really fast, especially when you're dealing with tons and tons of data.
So the more data you have, the more impressive it gets.
Exactly. It scales really well. And what's even more impressive, at least to me, is the space complexity.
Okay, space complexity. Now we're getting really technical. Break that down for me.
So for the iterative approach to binary search, it has something called O1, space complexity.
O1, that sounds very official.
Right. It sounds fancy, but what it really means is that it's super efficient with memory. It doesn't hog up a ton of resources. And that's super important in the programming world.
So it's like the eco-friendly algorithm.
Exactly. It gets its job done quickly and without wasting resources. And that efficiency, that's what makes binary search so powerful. It's used everywhere, from those massive scientific databases to, believe it or not, those price range filters you use when you're shopping online.
No way. So when I'm trying to find the perfect pair of shoes within my budget, binary search is my new best friend.
You got it. It's working behind the scenes to help you find what you need quickly.
That's incredible. It's like having a superpower for finding information. Speaking of navigating through landscapes of information, the cheat sheet, it then dives into graph traversal algorithms, and it mentions two in particular, depth first search, or DFS, and breadth first search, BFS. What are those all about?
So these algorithms, they're all about navigating relationships and connections, and not just in a social media kind of way, although that is one example. They're used for everything from mapping out how diseases might spread to, like you said, understanding social networks. It's all about the connection.
It's like mapping out the invisible links between things.
Exactly. So with depth-first search, imagine you're exploring a maze, right?
Okay, I'm picturing a maze. Go on.
So with DFS, you'd go as deep as you can down one path before you even think about backtracking.
So it's fully committed to that path no matter what.
Yes, until you hit a dead end, and then you back up and try another path and so on. It's like you're determined to explore every nook and cranny before you move on to a different section of the maze.
So DFS is like the meticulous explorer of the algorithm world.
That's a great way to put it. And the cheat sheet even mentioned a few specific ways it's used.
Yeah, like detecting cycles and systems. What does that mean exactly?
So a cycle is basically like a loop, right?
Okay, I'm following.
Like, when you get that annoying feedback in a sound system, that screeching sound?
Oh, yeah, the dreaded feedback loop.
Exactly. That's a cycle at play, and DFS is actually one of the tools that can be used to identify those.
So it's like a cycle buster.
Exactly. It's also used in something called topological sorting, which sounds very official.
It does sound very official.
But it's basically about figuring out dependencies. Like, let's say you've got a bunch of tasks to do for a big project, right?
Right, like a to-do list on steroids.
Exactly. Well, some tasks might depend on other tasks being finished first, right? Topological sorting helps you figure out the order you need to do everything in so that it all gets done in the right order and you don't hit any roadblocks.
So it's like DFS knows how to get things done efficiently in the real world, too.
Precisely. It's about understanding those relationships and dependencies. Now, BFS, on the other hand, breadth first search, is a little different.
Okay, so if DFS is the meticulous explorer, who is BFS?
BFS is more like, how should I put it? Imagine you're searching a building, but instead of going down one hallway until you hit a dead end, you check all the rooms on one floor first, and then you move on to the next floor.
Oh, I see. So it's less about exploring every nook and cranny and more about covering all the ground on one level before moving on.
That's a great way to put it. The article used that exact analogy, searching a building floor by floor.
That makes a lot of sense. So what kind of real-world superpowers does BFS have?
This approach makes BFS really, really good at finding the shortest path in a network. It's all about efficiency and finding the most direct route.
So like GPS navigation systems, that kind of thing?
Exactly. GPS relies heavily on algorithms like BFS to figure out the fastest route to your destination. It's constantly calculating, taking into account traffic and all those factors.
It's like BFS has an internal compass, always pointing toward the most efficient path. Amazing.
It's kind of like having a superpowered GPS, but like right in your head, you know?
Okay, I like the way you think. So it's not just about finding any old path, it's about finding the best one, the most efficient route.
Exactly, exactly. And especially if you need to like factor in all those things, like traffic or road closures, that kind of stuff.
Right, right. The real world stuff, it's like it knows how to navigate those annoying detours.
Exactly. It's
Yeah.
all about optimization, finding that optimal path.
No, the cheat sheet. It mentions something about non-negative edge weights. What in the world does that mean?
Oh, yeah, good catch, good catch.
Yeah.
It's getting into the weeds a little bit, but basically,
Yeah, decode that for us.
so edge weights, they're like the cost or the distance between those points on a map on that network, right?
Okay, got it. So like how much effort it takes to get from one point to another.
Exactly, exactly. So a non-negative edge weight, it just means that those connections between the points, they have to have a cost that's, 0 or more. You can't have like a negative distance in the real world.
Right, unless you have a time machine or something.
Exactly. So it's basically just a way of saying that the algorithm, it works in the real world with real distances and costs.
Makes sense. So Dijkstra's algorithm, this is running behind the scenes of like all those navigation apps, helping us get where we need to go as efficiently as possible.
All the time, all the time. And it's not just about getting you to your destination on time.
Oh. What else does it do?
Think about like network routing protocols.
Yeah.
How all that data gets zapped around the internet, those data packets.
Right, right. The information superhighway.
Exactly. Well, Dijkstra's algorithm, it's a key player in making sure that all that data, it gets where it needs to go in the fastest way possible. It's optimizing the internet, basically.
Wow. So it's making sure that, my cat videos and everything else, it all arrives on time.
Exactly, exactly. It's the unsung hero of the internet age.
I love it. Okay, so we've talked about finding things quickly with binary search, and now we've got Dijkstra's algorithm for finding the best path.
The optimal path.
The optimal path, right. But what about, those times when we need to, like, bring order to the chaos, when we need to sort things out? What's the algorithm for that?
Well, for that, we've got a couple all-stars.
Yeah.
Quicksort and merge sort. They're like the dynamic duo of sorting algorithms.
Okay, so tell us about these sorting superstars.
So they sound very technical, but believe me, they're not just for computer scientists. They're actually used like all the time in ways you probably don't even realize. Think about like when you search for something online, right? Or you're looking at a leaderboard in a video game.
Right, right. It's all organized from top to bottom.
Exactly. All of that is being sorted using these types of algorithms. They're what make it possible to make sense of huge amounts of data and present it in a way that's easy to understand.
So they're like the organizers of the algorithm world.
Precisely. Now, Quicksort, it's known for its speed. Especially when you've got tons and tons of data to sort, Quicksort is often the way to go.
So for those really big data sets, Quicksort is the go-to.
Exactly. It uses this strategy called divide and conquer.
Divide and conquer. Okay, I've heard that before, but I'm not sure I fully understand it.
So imagine You pick one element in the data set, right? And you use that as a kind of pivot.
Okay, like a central point.
Yes. And then you arrange everything else around that pivot. So anything smaller than the pivot goes on one side,
Right.
and everything bigger goes on the other side. And then you just keep repeating that process, breaking it down and sorting until, boom, you've got a perfectly sorted list.
Ah, so it's like strategically breaking down the problem into smaller, more manageable chunks.
Exactly. And merge sort, it's also a divide and conquer kind of algorithm, but it's got its own unique strengths. The cheat sheet mentioned that it's particularly good when the data is already somewhat sorted.
Oh, interesting. So it's like it appreciates a little bit of pre-existing order.
Exactly, exactly.
Ah,
Think about like databases, right? Where new information is often added in a way that's already somewhat ordered.
right. It's not just totally random.
Right. And in those cases, merge sort, it can really shine because it can take advantage of that existing order. It's also known for being very consistent. Its performance is like reliably good.
So it's the steady, reliable one.
Exactly. You know it's going to get the job done efficiently no matter what. So quick sort, that's for speed, especially for huge data sets. And merge sort, it's the go-to for consistency and for those situations where the data already has a bit of a head start in the organization department.
Okay, I'm loving these analogies. So we've got our navigators, our organizers. What other amazing algorithms await us on this cheat sheet?
Well, now that we've talked about finding things quickly and putting them in order, let's talk about finding the best path. For that, we have Dijkstra's algorithm.
So Dijkstra's algorithm, it's like it's finding the best route, but not just on a physical map, right? It's like it can map out the best path through any kind of network.
We got it. It's all about finding those optimal paths. And yeah, it doesn't have to be a physical map at all. It could be like a network of relationships or even just a series of decisions, like in a game or something.
Oh, that's interesting. So like if you're trying to figure out the best sequence of moves to win a chess game, Dijkstra's algorithm could come in handy.
Exactly. It's all about analyzing those connections and figuring out the most efficient way to get from point A to point B, whatever those points might represent.
That's so cool. Okay, so we've got our algorithms for finding things quickly, for putting them in order, and now for finding the best path. What else is there?
Well, let's not forget about dynamic programming. That was a big one we talked about, remember?
Oh, right. Dynamic programming, that was the one where you break down a big problem into smaller problems, right?
Exactly. It's all about breaking it down into those manageable chunks. And then, here's the really clever part. It remembers the solutions to those smaller problems, so it doesn't have to keep recalculating them over and over again. It's like having a photographic memory for problem solving.
That's amazing. It's
Um,
like it learns as it goes.
exactly. And that makes it super efficient, especially for those really complex problems where you might otherwise get bogged down in all the details. It's used in everything from like, figuring out the best way to allocate resources in economics to analyzing DNA sequences in bioinformatics.
Wow, so it's like a master planner and a super sleuth all rolled into one.
You can say that. It's definitely a powerful tool to have in your algorithmic arsenal.
I'm starting to realize that these algorithms, they're not just like abstract computer science things, they're actually woven into like so many aspects of our lives, even if we don't realize it.
That's what I love about this field. Once you start to see the patterns, you realize just how fundamental these algorithms are. But it's not just about the technology itself, it's about the problem-solving mindset they represent.
What do you mean?
Well, think about it. Taking a step back, breaking down a complex task into smaller steps, looking for those repeating patterns, optimizing for efficiency. Those are all valuable skills no matter what you're doing, right?
That's so true. It's like whether you're writing code or, just organizing your day, these algorithmic principles, they can actually be really helpful.
Absolutely. It's all about thinking systematically and finding elegant solutions.
I love that elegant solutions. Okay, so to wrap things up, we've covered a lot of ground in this deep dive. We started with binary search, the king of quickly finding what you need in a sea of data. Then we explored the world of networks with depth-first search and breadth-first search, those intrepid explorers of connections.
And we can't forget those sorting superstars, quicksort and merge sort, bringing order to our data-driven world.
And then there was Dijkstra's algorithm, our trusty navigator, always finding the most efficient route. And of course, dynamic programming, the master planner, breaking down those complex problems into manageable chunks.
And the amazing thing is, this is really just the tip of the iceberg. There's a whole universe of algorithms out there, each with its own unique strengths and applications.
It's like a whole secret world waiting to be explored. But hopefully, even just this little taste of the algorithm world, hopefully it sparks some curiosity for you, our listeners.
Absolutely. And if you're out there, preparing for those tech interviews, just remember, practice makes perfect. Dive into the code, experiment, have fun with it. You'll be acing those interviews in no time.
And even if you're not interviewing, it's just, it's pretty cool to take a moment and appreciate all those algorithms that are working tirelessly behind the scenes, making our digital lives possible. They really are the unsung heroes of the digital age.
I completely agree. They're quietly making everything work, from the apps on our phones to the internet itself.
Hmm.
It's pretty amazing when you think about it.
It really is. So, as a final thought for you to ponder, where else do you see algorithms at play in your own life? Food for thought.